All right, so now we're getting further in with our prac. So we've collected our data, we've put it in some sort of table, and now the question is, what are we going to do? So this analysis part, so analysing, one of the best ways in physics to analyse stuff is graphs. All right, so first paragraph sentence there is what do you do with it? Now, so there's a number of things here. You can have graphs, you can use it for calculations, etc., and you might have more tables. But as it says here, graphs are very useful. They give a visual relationship between the variables. So you can see what's going on. You can see whether it's curvy, you can see whether it's straight, and so on. All right, so there's a whole bunch of different things that you can get from the graphs. Now, these things, they must have these things. You've got to have a title. You've got to have scales. You've got to have labels on the axis to show what they are. This here I'll get to a little bit later, but really you should get them to start at 0. All right. You need to have your data points there. Line of best fit, if you've got a line of best fit. All right, line of best fit. And if you've got more than one graph, you need to have it numbered, because then you're going to refer to that graph when you are doing your discussion. All right, so analysis is not the same as discussion. So analysis is, what do you do with the data you've collected? All right, so we're going to analyze that data. How are we going to analyze that data? Well, in this, what I'm talking through here, we're going to analyze it by drawing a graph. And of course, you need to be neat. You've got to be neat. So what I'm going to suggest here is you use some sort of technology these days. We've got some sort of technology that we can use. So you probably should use that. That's going to give you the best graphs. And there's other benefits of technology that I'll get to. All right, so in this, we're focusing on continuous data, because that's pretty much what we're going to be collecting. We're going to be collecting continuous data. So data will need to be graphed. Scatter plot is the type of graph. All right, and just the points. We don't want the points joined up. We just want the points. It would be very rare in physics that you would use anything other than a scatter plot. All right, as it says here, you can plot by hand or using computer software such as Excel. I'm only talking about Excel because that's what I know how to do. And on Physics with Synno, there's a couple of description videos. There's some videos and also some how-to sheets. And if you're accessing this video, those two videos will be directly above this one. All right, so why am I talking about it? I'll just talk about Excel, but there's other graphing software. All right, so if you've got other graphing software that you use, then by all means use it. In Excel, I'll just talk about that because that's the one I use. So you can store your raw data in a table. All right, and in fact, if you're going to graph it, you're going to need that. But you should, your logbook or your scribblings in your logbook, you should end up with a table that you're going to do. Also, other things, if you need to do some calculations that you're going to do a number of times over and over, you can use Excel to do those calculations. Graph the data, and because we're going to be looking for relationships between variables, okay? So a graph will show us whether there's a relationship or whether there's not a relationship. All right, so Excel call it XY scatter. We can also put a line of best fit. In Excel, they call it a trend line. Again, in the videos about Excel, I'll go through that and show you that in detail. And then there's these other things. You can get it to find the equation for you. So again, that saves you a bit of work. Coefficient of determination, or Pearson's correlation coefficient. The Excel can work out those, and they're very handy, and I'll talk about that in a minute. All right, and the other thing is error bars. So errors, we need error bars, and Excel can put them on for us. And again, as I said in the video, the one directly above this one, I think it is, it talks about how to do error bars specifically. All right, now I already mentioned this. Instructions on how to use Excel can be found on the sheet using Excel to create graphs. There's actually 2 sheets now. There's another one, second one, in the physics with Synno. Let's bring it up. So here we are, practical investigation. Now this is the area I'm talking about. Graphing data using Excel instruction sheet follows on this graph. This video, I should say, goes right from the start, from a table of values all the way through. It does do error bars in this one, but I fluff around a bit using it, finding it, because I forgot what I was doing. But anyway, you get that. But then this next one down here, this instruction sheet and this video are specifically about putting error bars in, and this is actually a better, I explain it much better in that video than the one above. All right, and so this video that you're watching now, when it's finished, will go just in here, which is along with this document that I'm talking about. All right, let's get back to that. So here we are. Now, sometimes you've got to watch with Excel though. Sometimes it gives you things not how you would like. So one of the things that Excel does, the default settings, is it kind of zooms in on your data as much as possible. Now, you'll see here, this is starting at 1.4. Now, I mentioned up here, where did I said start at 0. Now, you can get Excel to change that so that you can start at 0. So that's what I've done here. And I've looked here. And so now I'm starting at 0. And these are exactly the same pieces of data. Now you can see that the one on the left makes it look like there's big changes. So as the mess gets heavier, the time goes down and it goes up again. It's what it looks like. When you start at 0, it still looks the same, but when you look at the line of best fit, it's all very, very close, so it's not much in the way of a change at all. Now, then we can get our equation, which is here. Now you can see here with this, I'll scribble up here, y equals -5 e to the e minus 5x plus 1.498. Now, this e to the minus 5x, or this one, this bit here, that's the way Excel writes 5 by 10 to the minus 5. Now, it's a negative gradient, so it's -5. Now, 10 to the minus 5, actually, let me do it down here. If I move 1, 2, 3, 4, 5 decimal places, so that's that number there. So there's 4 zeros and a 5. So, and of course, what we know from y equals mx plus c, then that number's the gradient. Now, that's a really small number. Okay, so like 100 thousandths, thereabouts. 50, yeah, in tenths, hundredths, thousandths, 10,000ths, 100,000ths. So it's just 500,000ths. It's a really small number. So a gradient of 500,000ths is pretty flat. Doesn't look pretty flat here. On the right, it does look pretty flat. Now, the other thing is this r squared value here is what's called the coefficient of determination. And for things which have gradients which are close to zero, it doesn't work very well. All right, because normally we're looking for a number close to 1. But for things where the gradient's really close to 0, that number there for the r squared gets closer to 0 as well. Don't want to go into the mathematical way of how that's figured out, but Excel does it. So in this one here, what I'm getting about too is really what this shows us is, and probably within the bounds of our errors in what we've done, what we've been able to do, depends how we measure our time and our mass, within the bounds of errors, of what we can say is that actually changing the mass doesn't change the time. All right, and when you look at your number on the end, C, and that's where it intersects the time axis in this case, would suggest that it's around 1.498. All right, so I just talked about that. Yeah, what I've written there is all the same as what I've just said. All right, so our conclusion from that would be that, you know, the mass doesn't affect the time. Affect or effect, I don't know. Effect the time. And in this case, you'd say something along the lines that the time is about 1.498, and then we'd need to look at how many decimal places were in our data, and then we'd need, of course, to round it off to that, or things to that effect. Now, what you would also add in there when you are doing your discussion that I'll get on, you would actually refer to that graph. So graph number 1 shows, and blah, blah, blah. All right, so, but that's getting on to the discussion. So the analysis is the graph, basically. That's essentially, that's it. You've taken your data, you've done something with it, so therefore you've analysed it. All right, and so now when you're looking at what your analysis shows you, that then goes into your discussion. And I've already, towards the end there, talked about down the bottom here what this analysis shows you. All right, so as always, have fun, and if you need assistance, make sure you grab hold of me.